I'm Lachlan, I'm the treasurer here at CCHS. My wife has been teaching like all year on Wednesday nights, so I haven't been able to get in here, but over school holidays I'm really looking forward to getting a solid education on MicroPython and obviously what's happening in the whole hardware world. That's a really useful summary, Matt. So, yeah, first probably just go through a couple of things that are happening at the hackerspace. We've recently just got a couple of grants from the Burundara Council, which is the council for where we are here. One of them involves taking the self-driving cars, which Andrew Fisher and Andy Gellman and others have been working on. The donkey carts out to the Kew Traffic School next year. And we've already had some interest in doing I guess some outreach with the Guide Dog Association and also this Probus group's interested, and also the autism group Learning for Life expressed an interest, and so we're just going to try and work with these people and see how they could be possibly part of what we're going to try and do. Had a really positive response from council, and I think what that means is probably next year we'll go for a grant which does formally involve these kind of groups, and it's also possibly an opportunity to get some triennial funding, which would kick in the year after for something where we actually get some proper funding into the space and possibly some staff to help with this kind of thing. So that's self-driving cars. We've also got a grant for a pick and place machine. And as what happens as soon as you finally get a grant for a pick and place machine, someone else has also offered one. So it looks like we're going to have 2 pick and place machines in the coming months. Andy's also picked up a couple of the robot arms which came from Melbourne Polytechnic, and they were moving them on, and for a nominal donation we've managed to secure those. Having dual robot arms, I think, offers all sorts of potential, so hoping we can do good things with those. And so because we've got quite a few hardware donations and things happening, we're also looking at possibly running a little, like a Christmas advent calendar where like each day we reveal a different donation to CCHS. So if anyone's got any ideas of other things they'd like to donate or something they're finished with, feel free to nominate it. Just send an email to the committee and we'll chuck it into the mix. So over the next month we'll hopefully just run through what's sort of going on, because we haven't really had time to sort of. No, Andy and Steve, I think you were over in China, was it? Yeah, so you guys have been busy with that, and so we haven't really had time to catch our breath. Andrew Nelson and Adric here had the SourceBot running at the weekend Bunnings Barbecue, which had about 4,000 likes on Facebook, and worked a treat, worked all day, pumped mustard, which is kind of we struggled last time. We got 1 or 2 just tomato sauce things before the thing just decided to clog up and stop dispensing.
So just for people who don't know what the SourceBot is?
Yeah, so the SourceBot, it's a modified cruiser printer, and it's got 2 peristaltic pumps which have been custom made at CCHS for dealing with viscosity of mustard and tomato sauce, and successfully and satisfyingly putting a pattern down onto the sausage. So the tomato sauce basically puts out a square wave, what looks to us like a square wave, and the mustard's just a dead straight line. You get a straight slow line of mustard. So there's a video on YouTube. We'll put that in the presentation for you guys to follow up, and. But more importantly, just great to see a project like that finally get out there, do the public outreach, which some of these things we get going in here, but we don't get a chance to demonstrate out there. So
there were people queuing up, waiting in line to put their dog in the sauce.
Yeah, that's right, and just and people doing it over and over. Not enough mustard, so you just go back and do another pass. And clearly, having in the version 3 feature requests, there's all sorts of things ranging from barbecue sauce to being able to write your name, I guess, would be the ultimate. Type your name and have it typomatically write the name of the source, typographically write the source. So that's what's happening. There's heaps happening at the moment, and we just haven't had a chance to really document it all. But we thought maybe just doing an advent calendar might be a way where we can just focus on one thing per day over a couple of weeks and get the news out there. So that's CCHS at the moment. I'm going to talk to you today. We've got a bit of an exclusive in that we've got one of the early Propeller 2 chips.
Yeah.
So these are these have been like 8 years or more in development. I think it's actually 13 years, and you can pass it around. But this is one of the first 10 chips off the on semi-press, and you know, until probably a day or two ago, these were like the only 10 around. And we've been tracking this project closely for about 8 years, and so we finally, you know, see real silicon. You'll notice that the chip's not like a plastic package; it's called what they call a blob top, and that's just a pour of epoxy. Like they just layer it over the top, and you can actually see where the die is if you look closely. It's got like a 10mm squared die. And so our 10 years of following this project is now about to turn into a whole lot of pain, because we're no longer waiting on somebody else to do something. We've got to make inroads with it, and we suddenly realised that you know, we Brian, my colleague Brian, and myself, we program in assembler, you know, because we don't mind it, and but we realise we really need a high-level language, and so we're looking around and saying, okay, we don't really like C, either of us, and so we're thinking, okay, yeah, so we're sort of thinking, okay, maybe Python's a good option, and so we're you know, we're sort of pretty naive in this Python world, but we're going to try and learn over the coming months and see what we can get going, see if we can get this thing up. And I did Andy's Jupyter Notebook course with Silver Pond, and so that, you know, had me convinced that, yeah, Jupyter Notebooks are great, you know, and got a lot of potential for the kind of data work we want to do with this chip. Tell
us about the chip.
Yeah, so I'll tell you about,
a lot of people might not know what Propeller is.
Yep, so Propeller, going back a couple of steps, so it's by Parallax, a company that brought us a basic standard in the 90s, brought us a Propeller 1 chip in the mid-2000s. Like the Propeller 1, Propeller 1 went open source at that same open source conference you're talking about a few years ago, so there's, you know, open source Verilog for it nowadays. So it's one of those few chips like the SI5, which you can get, you know, the real thing plus the open source if you want for it. The Propeller 2's been in development pretty much since that Propeller 1 came out, so that goes back now 13 years. And we realised probably about 8 years ago that it really works well on sine waves, which is what a lot of my work is around. And so that's why I've been so interested in waiting for it to come out, and not particularly swayed by other hardware offerings recently. So the key thing this does well, I'll jump to, is it's got a hardware Goertzel algorithm, which is like a DFT on the data streams coming into it, and so you can sort of pluck out that data, that sine wave and AC data, a whole lot easier than you'd have to code it on other chips. But this sort of takes it a level, another layer of abstraction, I guess, where you've got that sort of an analog layer above what we normally get on an A to D converter. Yeah, so coming back to the raw specs, which you guys would be interested in. So 512K of RAM, no flash on board. It's got an external flash chip. It's got boot from the external flash or from a micro SD card. And what else have we got? Megahertz or MIPS. So 8 cores like the Propeller 1, 8 32-bit cores, and around 70 MIPS rated each, and so that gives you about, I think it's 720 MIPS as standard, but the thing overclocks effortlessly to about 1500 MIPS. You know, that's what we've had so far without sort of modifying power rails and things on it. So, so it's sort of around Raspberry Pi 2, roughly, I think, roughly. Yeah, so reasonably potent. Because they've realised that it clocks faster than they thought or they designed it for, they're now sort of stuffing HDMI into it. So you've got 8 cores which can potentially do HDMI or other types of video, you know, your VGAs or your 4Ks or composite or whatever. Yeah, so that's the basics on it. I'll just grab my notes because I'll forget something otherwise. So So we did MIPS, oh yeah, okay, the memory. So that 512K has what they call an egg beta memory. And basically the way that's done, if you imagine like speed dating is probably the best analogy I can think of. You've got like your memory organised by its least significant bits, so you break it down, you've got everything which ends in 0 or 8 at one interface, and then you've got everything ending in 1 or 9 and 2 and 8, etc. And you rotate that against the 8 cogs, so on every rotation, every cog has got access to a memory slot, but it's in a kind of linear sequence. And so what that means is, like, on every clock can take a linear read. So if you've got sequential data, they can all be taking that sequentially. It's just that you've got that initial start offset, so you might waste a couple of cogs initially, but once you go, you can just keep going in a straight line. I think they use that on video cards as well, some of the video card designs. Yeah, 3.3 volts, 100 pin QFD, as you see on the board there. That's the basics covered. For the advanced stuff, as I was saying, it's got the background hardware Gertzel transformation, which is really good for converting AC signals. So the famous thing the Gertzel's used for is like DTMF decoding, like on the phone systems. So where you're just trying to extract one known frequency, or a row and a column kind of data. That's kind of a really basic use for it, though it's really useful for anything where you've got to try and read in AC information, and so the longer you stare at a signal, the better you can get that sort of phase and power resolution. The other nifty thing, one of the other nifty things it can do, in every single pin's got these smart pins, and every single one's got the same circuitry, and so your A to D is actually tied to your pin pad driver. So every pin's got an A to D on it. It's also got 5 different DACs in total, but for different impedances. And what you can do is you can run both of those together, so you can actually have like a DAC outputting a signal which is heading towards a monitor, and you can read in the A to D at the same time as you've got that, so you can see what's loading or what's happening, possibly do things like time domain reflectometry. You can also do things like power supply. Obviously if you set an output voltage on your DAC, you can watch as it loads to see whether you need to correct something. What else have we got? The lookup tables, there's internal lookup tables which are used for video, also sign generation, etc. The A to Ds can work above and below the rails, so they extend a little bit down below. So you can put a scaled bipolar signal into the chip and read it a little bit below the rail and above. Basically the 0 volt, like if you put 0 volts in, you can actually read something like 12%, 15%, I think, of the scale. So you got, and what happens is as you go further down below the rail, you'll get the body diodes start to conduct eventually. So you kind of got a slightly non-linear thing, but in a good way. You can put a larger signal in and sort of self-compensate it out. It's got a hardware codic, which is like a pipelined, multi-stage pipeline thing where you can pump in say coordinate rotations if you want to do rotations, or transcendental functions like trigonometry or logarithmic square roots, etc. You basically pump one of those in and 36 clocks out later it comes out, but you can pump in multiple values, obviously lots in the pipeline, and get other ones out. Brian will do a demo later. We've got a demo which is sort of blends VGA with the Cordic. It's called Cordic bugs, and it's got these little slightly AI bugs which run around the screen and try to avoid each other. It's just a way of proving and testing the Cordic functionality. It's got streamers, which are basically like a DMA kind of channel on each cog. So you can have, on each sample, you can have a 32-bit, up to 32-bit transfer from hub memory out to the pins, or to the lookup table if you're doing sort of video stuff or sign wave generation, etc. So I got one of those on each core, and they're not only 32 bits, but sort of the 8 and 2 and 4 and 1 bit, if you want to use it that way. So really good for logic analyzer kind of things. If you want to construct a logic analyzer, and of course you can stream the A to D data stream if you want to as well. Strong community involvement in getting this thing together. There's been a lot of contributors, been very open source, like very open development process, everything including the prices they pay for the chips and all that sort of out there in this in the forums or online. A lot of Australian contributors, and you know, a guy up in Brisbane who designed that board, which we passed around. There's a guy in Sydney who used to work for Netcom. There's about 4 of us who meet regularly here in Melbourne. As a result, we actually had a meeting here about 4 years ago at CCHS, and then we've kept sort of meeting at the pub every now and then. And now that the thing's out a bit more regularly, the HDMI, there's a guy working locally on that for getting that into the next revision, which will be a few months away. And yeah, certainly a few of us doing field testing around here in Melbourne. So yeah, so that's all the kind of advanced stuff. A little bit about the projects we're working on. Brian here's worked on a pretty nifty logic analyzer, just testing out that streamer functionality. I guess we're just trying to push like each aspect of the chip because it's not really well proven out yet. Yeah, so logic analyzer, Cortic bugs we're talking about. It's got the Space Invaders program, which is kind of a probably shows our vintage more than anything, doesn't it? Yeah, and the spinning demo, graphics demo where it spins the thing around, which has been useful for sort of overclocking testing. There's a real wall of failure where everything fails at the same frequency, and once you hit it, yeah, it's quite spectacular. When you've got the video going and you can sort of see, oh yeah, some of those cogs are just on the edge of being able to copy data across, and it loses its ability to rotate, stuff like that. So just speaking about a couple of other projects, Brian's working on a theremin as well, because you've got all that analog stuff internally, there's not a whole lot of need for like your biasing components and all that kind of stuff you used to, like doing, say, resistive DAC, that's kind of out the window. So, you know, we're hoping there's a lot of demos we'll be able to do which just involve wiring, you know, just electrodes and wiring. I want to work on a project here which is called sort of reinventing the wheel, where we've sort of got, if you imagine like 64 spokes with each one just hooked up to an I/O pin, so you can have capacitive sensing and all that. So as the thing rolls, it can sense like when what spokes are near the ground and which spokes are near a person or a step or something like that. So and then use that information to control other things like rotate a screen, so the screen always stays in the same rotation as one of those round 4D displays, etc. We want to do like a jelly-based IMU, so you've got to imagine a cube of jelly, and as you move it, it kind of is going to resist that or go the other way. And so if you detect that capacitively, you've got a sort of an IMU which kids can relate to, rather than the MEMS scale stuff which we're used to, but just have something which is that kind of tactile, I guess. And yeah, other industrial stuff which we can't really do on the vid, but happy to talk about later. So yeah, so just in summary, what we're trying to do, we're keen, if we can, to try and get something going on the MicroPython front with it. As I said, that's sort of born out of the pain of either continuing programming in assembler. We've got some stuff out there which has worked, we're quite happy with, but it just took way too long to develop. And so we're looking at what the other options are, and we're happy to sort of put some time and effort into it. Obviously, we're really well exposed to the architecture, but doing something like that for our cores, I guess we'd want to look at what's been done on other what's been done on other multi-core systems. It's got some good bytecode friendly instructions, and our first thought is, I think we talked to you about, is try and build a like a bytecode executor kind of thing, virtual machine kind of thing, but that's only because we're coming at it from an assembler point of view rather than knowing all the C tool chains and all that kind of thing. So yeah. Anyway, look, that's about it, guys. So yeah, if there's any questions, just feel free to ask now or later or whatever. And over the coming months, we'll be sort of around here for a while and using it in the space for various stuff to see how it goes. So, yeah.
So Brian, you'll be demoing it after the talks? Is that?
Yeah. Do you want to get it loaded up?
Yeah, I'm fine.
Yeah, and maybe we'll get. Damien's got a couple minutes to talk about some SP32 changes.
So it's thanks,
Lachlan, is that going to?
No, that's
like
okay.
right now? Or?
Yeah, no, go now, and then we'll come back to this.
Well, first of all, can I say thanks? That's awesome.
Yeah.
Awesome to see the perseverance. So, geez, long project.
Each bug is hammering the Cortic engine, which is doing all the transcendental stuff. So basically, each bug has a narrow vision. It's looking ahead for another bug in the way, and depending on how close it gets, depends on how hard it reacts. It turns away. There's 2 video frames that are being built, so it's just doing one frame and then it's alternating to the next, going back and forth. So they're not sprites, it's just drawing straight pixels there. The Cordic, as Lachlan mentioned before, is a pipeline. So I've got multiple cogs that are doing, or multiple cores that are loading into the Cordic, and they're just waiting their turn and they get their data off in the end. And you can interleave them as well. So you can load something into the Cordic and load off another thing into the Cordic and go off and do something else, and then come back and wait for the result to pop out the other end. So this is basically more of a torture test, just to make sure that the Cordic can handle multiple cores attacking it all at the same time. So yeah, that was the idea behind that demo. And the trails were basically just so you could see what sort of reaction they're having. Some of them overreact. There seems to be a weird thing that happens, not by design, that they ultimately end up going clockwise. I didn't design it that way, but it seems to be a weird quirk. But I've never actually investigated why that happens. But
Rounding error?
well, yeah, it could be. It's that might be a project for somebody else to go dive in and see what I've done.
Yeah, PhD kind of thing.
Yeah, it could be something to write a paper on that.
So you're doing just VGA out directly from the board?
Yeah, so that's driving VGA straight out from the pins. There's no components.
Wow.
It's just directly connected to a VGA connector. So the same applies with composite video or NTSC, anything like that. You just select the right resistor for the DAC, output, straight to a connector, and off you go. Same sort of deal with the analog in a lot of ways. Because you've got 64 pins, and all have got analog, it is possible to be reading analog on all pins all at the same time. And you can stream that data. It's a Sigma Delta ADC, so it's just bit streams. And the streamer can actually stream that into memory, and you can apply filters to it if you want, if you need to go higher precision or clean it up depending on how your board layout is. The beauty of the chip is that you're not locked into a peripheral only being on certain pins. Every pin's identical and every core is identical, so with your board layout you can say, well, I want this stuff to be out this side, so you just run those tracks out from those pins. You don't have to sort of worry about, well, the peripheral's only available on this pin on this side and route it around. So you've got this nice, I don't know if you saw the board when it went around, it just fans out basically. So yeah, it makes the board layouts just beautiful. And less components, because things like this VGA, it's just a connector. There's no components required. Just hook it up. So yeah, that's what we're loving about it as well. The beauty of having the multiple cores as well, obviously a bit like with your threading you're talking about there, is that you can just fire off, point it to a piece of code and say, right, you just run that, and it'll just run in the background. You don't even know it's there. It does actually have interrupts as well. The previous model didn't. And interrupts were put in, which if you're used to the old chip, it's kind of weird because it never had interrupts. But they're in there now to keep people happy. But any of these devices that are on the smart pins, you can have UARTs, there's synchronous UARTs, there's all sorts of counter modes, quadrature encoder is all built into the pins. So you just decide which pins that you want to use.
Yeah, did you mention USB? I don't know if you did.
Yeah, it's got low-level USB, so that potentially you can have 32 USB connections if you want.
How much are these?
That's a bit over the top, but
It's free. We haven't paid for it. So.
yeah,
No,
HDMI,
how
it's
much
not
they
in this
like?
current chip, but it's actually going to be in the next one.
$20.
That's just being developed at the moment.
But
Because
that's what
the
we-
chip exceeded expectations in speed, the clock speed was able to go up, and now they can say, well, we can pack HDMI in there now because we've got the clock speed for it. So it's
So our record's 372, isn't it?
yeah, we got the
Before it
record
falls over.
372 meg. It's only designed to do 180, and we've been told that we could probably get 400 without liquid nitrogen. But yeah, no, it's worked out to be quite a good little chip. It's got a very rich instruction set. It's not RISC. It's got about 350 instructions, different instructions in it. A bit hard to remember some of them, but some of them are tuned up for some of the specific functions. So, for example, the VGA driver there is about 30 lines of assembler for the complete VGA driver. So probably 10 lines of that is configuring it, 10 lines of that is actually generating the actual frame itself, and then there's just a few configuration bytes. So the streamers are very good with the different modes, 4-bit, 8-bit modes, so you can generate video easy. NTSC and the older stuff, PAL, nice and easy, just straight out on a pin. You can set the DAC up in 75 ohm mode, so no components again, just straight out to an RCA connector and off you go. So yeah, it's nice.
So just to update the status on where this is at right at this point in time. The guy who created it's a bit of a perfectionist. There's a couple of bugs in it, and one of them is that the composite video, there's a Verilog sign extension bug. So basically the colour burst stuff doesn't work. You can have grayscale NTSC no problem, but they're going for another revision, in a few months' time. And so right at this point, whatever we find, obviously we've got a chance of getting it in there, into the baked into the silicon. So yeah, we're just frantically trying to find what the issues might be. We haven't found a lot wrong so far, other than those known kind of issues. But we've got some ideas we've been talking about on how to just push it further. But a lot of the time we're finding the infrastructure and the instructions are already kind of there. It's just a matter of applying it in a different way.
But Python is the perfect fit for this.
Yeah,
chip.
we just believe it'll be good.
As much as it's been programming in the assembler for years now, and I'm used to it, but Python needs to go on there, I think.
Yeah, so Brian's been working on a debugger, for internal use mainly, but sort of matching all those instructions and being able to set breakpoints and things like that. And there's a few challenges with that, as you can appreciate once you get into the really finer detail. But he's written the front end for that all in Python on the PC end of it. And so as the thing's been tracking, whereas this thing's evolved over the last few years, he's been sort of having to update his debugger to match what's there, and that's found a few issues like early, which would have been baked into the silicon otherwise. So do you want to try and load up his pin? Can't do fuzzy yet. What about Vegas or? Actually, who wants to see the maximum number of bugs you can load?
What's the aim? So the aim is just to release this as a chip that people can buy and stick on the board and do what they want with it. Yeah, so that's right. It's to build. They've created this hopes and enjoys when people find cool stuff to do with it. So he's not particularly. He sort of hasn't really set out to conquer a market. I guess he's just made stuff which he likes experimenting with. Chip Gracie, he's a. You can go back to the open source conference a few years ago and hear him talk about it when they actually release the open source aspects of it. But he's interested in a wide variety of things. He loves things like the Gertzel transform, loves audio kind of stuff. So he made a vocal tracked demo, which sort of had on the previous one. There's this breathing demo, wasn't it? And the famous sort of 7 demo where it's actually synthesizing voice and breathing sounds through a voice box. So he just likes that kind of sort of interfacing with the real world kind of stuff, but not in the way we think of it in terms of interfacing to like an IMU or something like that. It's more low level, so that's hence the sort of interest in sine waves. He's got a good demo online where he's set up a sort of an air pointing kind of thing where he moves his hand around and it's sensing just through the capacitance in the air, so that kind of stuff, and all it's got is just electrodes, so that's why, the theorem I said to Brian, well, there's kind of all your hard work done on it, but there's going to be a lot of that kind of stuff, which, you sort of, your component count goes way down because all of a sudden it's sort of on the inside of the boundary of the chip, rather than what we used to, where we sort of construct these little external peripherals or matrices or resistive DACs or whatever. It's kind of changes your thinking a little bit because now it's on the software controller. Plus you've got 8 identical cores and you've got 64 identical pins, and so those kind of constraints where you say, okay, I don't have enough UARTs on this, or I don't have enough USB ports or whatever it might be, it's sort of that kind of, it's not really an issue, it goes away. The only thing we're slightly disappointed, it's got 8 cores in it. We were initially hoping for 16. We had big plans for 16. So we just have to use more chips, you know, it's kind of the thing. But, yeah. So,
high-level compilers yet?
oh, there's a couple of sort of what I'd call like solo contributor kind of efforts which aren't widely used or supported, and so there's people out there who have sort of made something for their own use and shared it, and it hasn't necessarily caught on. But that may happen now that there's actual silicon out there. There's about to be 100 engineering samples kind of released in the coming week or two, and so yeah, maybe, and you know, that's sort of from our point of view, we've now got to work out, you know, to bolt something like a PyBoard or something onto it which has got the Python component. Do we try and push, you know, how do we do a high-level language when we've got the passive side of it, the assembly language side of it is the only real option at the moment. So, and we know that works, but it's a painful, slow coding experience once you want to get going. So, yeah, so hence our interest in what we can do on the Python or MicroPython side. And I'm particularly interested also hearing about that, you know, what you guys are doing with Jupyter notebooks and things like that, where you kind of send out little snippets to execute. Yeah, so all looks good so far, but yeah, there's a sort of, we're in that twilight zone where, you know, if we came up with a really cool idea, we could possibly, you know, get it in there. There's a lot of resistance to change now that it sort of works mostly. You know, people say, well, don't mess anything up, but it's sort of verification that on setting synthesis capabilities and work to treat, you know, all that kind of, you know, sea of digital logic which they've put into it, and that wall of failure thing where it all falls over at 384 meg, you know, and 372 everything's fine, and at 384 you got it all falling over, going crazy. You know, it's just that sort of brute force computing where you throw, you know, synthesizer design. But it's been a really good project to track and just learn about, you know, how stuff's done, you know, what the price of doing ASICs are and all that kind of thing. It's been a real interesting trip. It's just taken that long. You know, it's kind of, and we also thought we had something back in about 2013 or 14. They sort of had an aborted earlier version, and they went back and sort of simplified a lot of aspects and complicated others. So.
What's the power consumption?
Yeah, look, it's sort of at rated, it's around 1. It's a bit over a watt, you know, sort of thing. So, but because everything's NCO driven, you got like a master clock, and it doesn't have to be like we've had we've had NTSC coming out down to 7.5 megahertz, you know, half the double color space, the double color burst frequency. So, you know, it's not great quality video by any stretch, but it still shows that you can actually go low and still get video out of it and things like that. So you've got a bit of flexibility. But it's going to be, I think it's going to have a bit of. It's like, you know, under rated conditions, I think you just need to have like a Raspberry Pi style vented case kind of thing. But there's going to be a whole lot of people who are going to go after the overclocking thing, where I think it's going to benefit from a bit of forced airflow. You know, just that's sort of my early take on it. But there's nothing really to be too afraid of. The silicon itself will run hotter. You know, but if you're worried about, you know, kids touching it or something like that, you know, I think it requires a little bit more thought. And I don't think we're going to see anything as compact as what, you know, some of you guys are putting out. So. You know, it needs a little bit of space and copper to spread the heat around. We've been doing a fair bit of testing with dry ice because we've been chasing like analog noise floors and things like that, and trying to, you know, find out what. Can't cast this yet, unfortunately, but you can see there it's the same design out of the icebox. It's come out, and there's a little. I don't know if you can see. There's a TO92 knob at the top, which is actually the temperature sensor, and that bottoms out at minus 57. We found, so you know, the sheet says minus 55. So. It comes fresh out of the box. It doesn't take long.
Jump out of the screen.
Oh, sorry.